The aims of this experiment are to determine the operating characteristic of different pumps in a contained unit and to understand the types of pump in principle and design, and the selection of the appropriate pump for a particular application for optimal operation. Multi-pump test ring is specifically designed for students' demonstration on the principal operating characteristic of different types of pump. The unit is supplied with two centrifugal pumps and a positive displacement pump. The unit incorporates appropriate pipework and tanks to make the operation self-contained. The manually operated valve and pipework are arranged for rapid and safe selection of any one test pump. Measurement sensors are included to monitor the pump speed, power, pump head, and flow rate. There are two broad classes of pump: positive displacement pump, which include gear pump, vane pump, and piston pump, have a fixed displacement of liquid per revolution. Rotor type pump, which include axial pump, centrifugal pump, and a channel inflow pump, generally work at a high rotation speed. The pressure difference between the suction and the delivery arises from the conversion of kinetic energy and pressure energy. There are several theories that are being used to determine the effectiveness of the pump use. The torque exerted by the motor is the product of the lever arm length and the product of the load cell. The load cell is calibrated by resting a known weight on the small ball bearing that presses on the load cell center pin after zeroing the display. The lever arm length in this experiment is the horizontal distance between the motor shaft center line and the button on the load cell. The power delivered to the belt and then to the pump is given by the formula P equals to 2 pi nt, where n is the rotational speed in revolution per second, T is the torque in newtons, and P is the volumetric flow rate and the pressure drop across the pump. The efficiency of the pump is then the ratio of the power absorbed by the fluid to the power supplied by the motor. With small pumps such as those supplied, efficiency may be quite low due to the factors such as friction in the bearing, turbulence in the pumps, and backflow in the gear pump. Gear and centrifugal pumps are very different in construction and operation. As a first approximation, a gear pump is a positive displacement device in the sense that it delivers a flow rate proportional to pump speed and independent of discharge pressure. In contrast, a centrifugal pump delivers a discharge pressure proportional to pump speed and independent of flow rate. In the present experiment, closing the ball valve in the centrifugal pump discharge line causes no problem, while closing the ball valve in the gear pump discharge line could destroy the polymetric gears.
Procedure consists 5 parts. Firstly, general startup, and the other 4 is experiment 1 until experiment 4. General startup. This step was taken to avoid any misuse and malfunction of equipment. The appropriate pump and flow meter were selected according to the following combination, which are Table A and Table B. Table B is the reference for all experiment, which is experiment 1 until experiment 4. Experiment 1. Rotational speed against volumetric flow rate. Experiment 1 is about performance curve for a centrifugal pump. The data collected will enable to plot the following characteristic curve: rotational speed against volume flow. Experiment 2. The performance curve for a centrifugal pump. The data collected will enable to analyze 6 characteristic curves. For example, pump total head against volume flow rate. Experiment 3. Rotational speed against output pressure. The data collected would enable to plot the curve of rotational speed against volume flow rate. Experiment 4 are the performance curve for a positive displacement pump. The data collected will enable to plot 7 curves. For example, volume flow against output pressure. At the end of the experiment, the potentiometer was adjusted to its minimum setting, which is fully anti-clockwise. The pump was switched off.
For experiment 1, we have table speed, rotational speed and flow rate for pump 1. As you can see, speed rotational per minute is inversely proportional to the flow rate. For analysis in experiment 1, we use percentage of flow rate and substitute into the equation to find the volumetric flow rate. As you can see in the table, as the rotational speed decreases, the volumetric flow rate is also decreases. A pump is a mechanical device used to force a liquid or a gas to move forward inside a pipeline or hose. They are also used to produce pressure by the creation of a suction, which causes the fluid to rise to a higher altitude. Pump also a device that expends energy in order to raise, transport or compress fluids. In experiment 1, the reading that was recorded in the table shows that when the speed is decreased, the reading of flow rate also decreases. Then, the graph of rotational speed versus volume flow rate is plotted. A straight line graph is produced. Volume of Q was calculated by using the formula as shown in the slide. For experiment 2, we change our flow rate and observe the speed, the differential pressure and the power of kilowatt. In experiment 2, the readings for flow rate, differential pressure, power and speed are recorded from the speed and output flow rate are maximum. When the output flow rate is decreases, the table shows that the values, differential pressure and speed increase while the power is decreased. For analysis in experiment 2, we converting the motor input power from kilowatt to watt by using the equation. From the table, we can see as the volumetric flow rate decreases, the motor input power is also decreases. Next, we need to calculate the pump total head by using the equation. The percentage of differential pressure are substituted into the equation to find the pump total head. And then, to calculate the pump power output, we need to substitute the volumetric flow rate into the equation to find the pump power output. And then, to calculate the pump power input, the power is minus by 70 watt to get the pump power input. As you can see from the table, as the volumetric flow rate decreases, the pump power input is also decreases. To calculate the pump efficiency, the pump power output must divided by the pump power input and times by 100 to get its percentage of pump efficiency. To calculate the overall efficiency, the pump power output is divided by 560, which is the total pump power input, and times by 100% to get the overall efficiency or percentage. For experiment 3, we have speed, flow rate, percentage of flow rate, and the differential pressure for pump 3. Analysis in experiment 3. To find the volumetric flow rate, we use the equation in the slide as shown in the slide. As shown in the table, as the volumetric flow rate decreases, the rotational speed is also decreases. In experiment 3, the readings for flow rate when there is a decrease in the speed is recorded. The formula of volumetric flow rate is shown in the slide, used to determine the volume flow. From the table, it is known that once the values of speed decreases, the values of flow rate and volume flow rate are also decreasing. A graph of rotational speed versus volume flow rate is plotted, and it shows a straight line graph, which means that the speed is directly proportional to the volume flow rate as set by the theory. As you can see the graph in the next slide, they are linear. And lastly, in experiment 4, our MV is pressure, and we observe flow rate, speed and power in kilowatt for pump 3. In this experiment, the readings for flow rate, differential pressure, power and speed are recorded from the speed and output flow rate are maximum. When the pump head is decreases, the table shows that the values of volume flow rate increase and the power is decreased. Pump efficiency ETA and the overall efficiency decreases when the pressure is decreased. Volumetric efficiency decreases when pressure is decreased. The graph for motor input power versus output pressure and pump power input versus output pressure show increasing curves, while pump power output versus output pressure gives a straight line graph. The volume flow versus output pressure decreases. Pump efficiency versus output pressure and overall efficiency versus output pressure show an increase. The graph of volumetric efficiency versus output pressure decrease. In experiment 4, as shown in the table, as the output pressure decreases, the volumetric flow rate increases. Next, we have a table of output pressure and motor input power. As shown in the table, as the output pressure decreases, the motor input power decreases. In this experiment, we need to find the pump power output, PO. To find the pump power output, we use the equation as shown in the slide and substitute the volumetric flow rate into the equation and find the pump power output. Next, they are shown a table of output pressure, percentage of output pressure and the pump power input in watt. As shown in the table, as the output pressure decreases, the pump power input is also decreases. And then they are shown a table of the percentage of output pressure and the percentage of pump efficiency ETA. In this table, we can see as the output pressure decreases, the pump efficiency is also decreases. Next, in the table shown in the slide, there are output pressure and the overall efficiency ETA. As shown in the table, as the output pressure decreases, the overall efficiency is also decreases. And lastly, in this experiment 4, we have table of percentage of output pressure and the percentage of volumetric efficiency ETA V. As you can see, as the output pressure decreases, the volumetric efficiency increases.
In conclusion, this experiment allows the students to measure the operating characteristics of different pumps in a contained unit. The principles of the pump are different from each other. Pump is a device used to move fluids such as liquid, gases by physical or mechanical action. The results show different types of curve and line graphs according to different pumps. The function, principle, and design of each pump vary according to its type. Different types of pumps hold different operating characteristics. From this experiment, it is proven that centrifugal pump, plunger pump, and gear pump has different working principles due to the type of fluid in which the pump is used to move the fluid. The design of three pumps has a big difference, as centrifugal pump and plunger pump need two motors to run the pump, while the gear pump only needs a motor.